I hope you have done the homework that I had asked you to do, namely find out the relationship between the steady state speed, the reference voltage, when we use the integral feedback. And as perhaps you should have expected, the relationship is very simple. The reference voltage value ER, let's say, the constant value of the reference voltage, is simply the tachogenerator coefficient KTG multiplied by the nominal or the rated angular speed of the motor omega 0. With this, then, the feedback voltage is exactly equal to the reference voltage. Therefore, the output of the difference device is 0. Notice that I am calling it a difference device and not an error detector. The output of the difference device is 0. This device feeds into the integrator, and as we saw earlier, the input to an integrator becoming 0 does not mean that the output of the integrator will be 0. In fact, previous to the input becoming 0, the input was non-zero, as a result of which the output of the integrator will reach a constant value. This will be the constant value which, when amplified, will become the applied voltage applied to the armature, which under rated conditions maintains the speed at the desired speed omega 0. And even when the torque changes, even when the load torque changes, the speed returns to the rated value after a transient period in which the speed will either drop or increase depending on whether the load torque is increased or decreased. So the advantage of using integral feedback in addition to the proportional thing K tachogenerator is that the steady state error for changes in the load torque, that is for disturbance change or a disturbance input, becomes 0 and not non-zero, unlike the earlier case when we only had proportional feedback. You notice that the gain of the amplifier, which amplifies the output of the integrator Ka, does not occur in this relationship at all. The reference voltage is equal to the tachogenerator coefficient multiplied by the angular speed. So it doesn't seem to depend on the gain of the amplifier. So even if the gain of the amplifier is simply 1, the integrator will produce enough output so as to make the motor run at the desired speed. Then what role is the gain of the amplifier playing? Now, as I mentioned to you earlier, what we have been talking about is only the steady state behavior, that is after the load torque was changed to a new value and then kept constant at the new value. What happens in the long run, that is if we wait sufficiently, let's say beyond more than 5 or 10 time constants of the system, this is what we will find. And the gain of the amplifier Ka plays no role here. But as we will see soon today, the gain of the amplifier plays a very important role in the transient behavior. That is what happens during this time when the speed is either decreasing or increasing from the rated value only for a short time, but still it is going to change. So in what way does it change? So what is the transient behavior? This will be determined by the coefficient Ka. Now to see that, I will redraw the block diagram of the system, and I want you to go with me very quickly so that we don't have to spend a lot of time repeating what we have done earlier. So in the block diagram now I am going to show, starting with the reference voltage with the plus minus difference device. The output, of course, that is to be expected is omega s, input is the reference voltage ER of s, and between the two you have the K tachogenerator coefficient, because that feedback we are keeping. The output of the difference device goes through an amplifier we combined with an integrator. In other words, 1 by s is the integrator action, Ka is the scaling action, and if Ka is greater than 1, then we are amplifying the output of the integrator. This output of the integrator becomes the applied voltage Ea of s. Now from that gets subtracted the back EMF, so I am showing it here as Kb into omega s. So that difference then determines the current, armature current, and the transfer function here was 1 over SLA plus Ra. That produces the armature current Ia, that is multiplied by the torque constant Kt. this produces the motor torque. Then we have another difference device. From the motor torque, the load torque is subtracted, so there is TL of S there. This difference is the torque which then overcomes friction or accelerates or decelerates the motor shaft. So in between we have a transfer function here given by 1 by Sj plus Kf. So this is the block diagram of the speed control system now. Let's go over it very quickly. EAR is the reference voltage. From that the tachogenerator output is subtracted. The difference is amplified and integrated. There is a combined action, 1 by S integration. Ka is the scaling, and which will usually be amplification, produces armature voltage EA. From that the back EMF subtracted gives rise to voltage that essentially drives the current through the armature inductance and resistance combination. So there is this block 1 by SLA plus RA that gives rise to the armature current. Kt times that is the motor torque. From that subtract the load torque. The difference is the torque available for overcoming friction and acceleration. So that going through a transfer function 1 by Sj plus Kf produces the output quantity, namely omega S. This is the complete system. Of this, note that this Kb block and this difference device is only conceptual. It is not an external thing block here, Kb, an external difference device. The motor action is such that there is the applied armature voltage and there is the induced voltage generated by rotation of the armature in the magnetic field, and that is where the difference action is taking place. Of course, Ra and La are also not physically concentrated resistances and inductance respectively, but the motor armature has a resistance. The motor armature behaves also like an inductance, and therefore you have that combination. Then Ia into Kt, Kt is shown as a separate block, but there is nothing physical like Kt. The armature current in the magnetic field produces a torque, and Kt is only showing the relationship between the motor torque and the armature current. Likewise, the load torque, although it exists separately, the motor torque, it may not be possible to measure it separately. However, again conceptually or in the model you have the difference between the two, and that difference accounts for either the acceleration or deceleration through J and the overcoming of friction through Kf. So this is the block diagram. Now what I am going to do is something we did earlier, and for the moment let us only look at the effect of ER, the reference voltage, that is when the reference voltage is present and the load torque is either 0 or we are not changing it. I told you earlier that the output omega S will depend on both ER as well as TL. So it depends on two things and not only on one thing. For the moment we will look at only the part that depends on ER, and then we will look at the part that depends on TL. In fact, we might even look at both of them, although separately, one after the other. So because of this, I am going to reduce, and this is something we did earlier using the Mason gain formula. I am going to reduce the effect of TL and the effect of EA, the armature voltage, through two transfer functions. So in other words, I am going to replace this part of the block diagram which lies between this EA, TL and omega S boundary by an equivalent pair of transfer functions, and this thing we had done earlier. If you remember, now if I am only looking at this part of the signal flow graph or block diagram, I have EA is one input, TL is another input, there is a loop, so I have to look at the loop gain. There is only one loop. I look at the loop gain, I calculate the delta corresponding to the loop gain, and then I am ready to write down the expression for the two transfer functions from EA to omega S and from TL to omega S. We have done this already, so I will just ask you to quickly go over it. So the transfer function from omega S to EA of S, or therefore omega S will be equal to a transmittance involving EA of S minus another transmittance multiplying the load torque of S. And what was delta? Well, L, the loop gain, was, if we go back to this, Kt, Kb and these two transfer functions which are first order factors. So L is equal to Kt, Kb divided by SLA plus Ra into Sj plus Kf, and because it is going through a positive sign and a negative sign. Kb is the negative sign, therefore this has a minus sign. So L is minus of that. There is only one loop, so delta is simply 1 minus L, or it is equal to 1 plus Kt Kb divided by SLA plus Ra into Sj plus Kf. So this is delta. So I'll write it here as the common denominator delta and common denominator delta for both the transmittances. And now the two separate numerators. In the case of Ea, the forward path is from Ea through this 1 over SLA plus Ra Kt through the other transfer function to omega, going with a positive sign. Now that will be multiplied by what remains of delta, but this forward path touches the loop, therefore delta for the numerator is only 1, and therefore what do I have here? I simply have Kt divided by SLA plus Ra into Sj plus Kf. For the load torque, the forward path only involves 1 over Sj plus Kf and with a minus sign, and that minus sign I have already put out here. So for the load torque, then I have to simply write here 1 over Sj plus Kf. So that's the expression we have for omega s in terms of Ea of s and TL of s. Note, both these expressions have delta in the denominator. The denominator is the same, the numerators are different. Now as we did earlier, we will simplify the expressions by getting rid of the fractions in the delta term, that is by multiplying by the two linear factors, and therefore we will get the following expression for omega s. Now this delta will change to something which will be common to both of them, right? So what will the delta change to? I will have this 1 plus this. Now when I multiply by this factor, I will therefore have SLA plus Ra into Sj plus Kf plus Kt Kb, and I am getting rid of the denominator here, so I have to multiply the numerator by these factors. Now when I do that for the armature voltage component, then I will get rid of the denominator altogether. I will have only Kt left, so I will have Kt into that. This whole thing multiplies Ea of s. Just check that it is correct. Minus the denominator of the second term will be exactly the same. The numerator now, the numerator was 1 by Sj plus Kf. Now I am multiplying that by SLA plus Ra into Sj plus Kf. So what will I have there? Only SLA plus Ra. The Sj plus Kf factor cancels out. So this is what the two transmittances from EL and TL of s to omega s look like. Both of them have the same denominator. Now if you remember, and of course if you don't, you can still look at it right away, that this denominator is going to be a quadratic. It's going to be a quadratic, and here of course the coefficient of s squared will be La into j. So if I divide both the numerator and denominator by that product, then the quadratic will look like s squared plus as plus b. You remember that quadratic we had looked at earlier, then we had looked at the roots, nature of its roots and so forth. So that's what we will get. So I'll write it again as omega s equal to, now for the EAS part, what will I have? I have this Kt, and now I am dividing by La into j. So I like Kt divided by La into j divided by s squared plus as plus b minus the second transmittance. This time I have SLA plus Ra, and I am going to divide it by La into j. So if I cancel off La, I can write this as, when I divide by j, 1 by j, and in the numerator I will have a factor left, and that factor, if you remember, was 1s plus 1 by tau a, where tau a is the armature time constant. This comes from tau a being equal to La by Ra. So the denominator is the same, but the numerator for the load torque transmittance is a little different. And if you remember, the denominator gives rise to two poles of the transmittance or the transfer function in each case, whereas for the transfer function from the applied voltage, armature voltage, to the speed, there is no zero but there is only a coefficient kt divided by La into j, whereas for the transfer function from load torque to the speed, there is not only a coefficient 1 by j, but there is also a linear term which corresponds to a 0. So we have two poles which are common to both the transmittances, but only the load torque transmittance has a 0. And so as we did earlier, one can draw the pole 0 diagram. In fact, I am going to do that very soon. But before we go to that now, I therefore have a system which can be represented as follows. Now from EA and TL to omega, I am not going to show all those different blocks. I am going to show only these two blocks. And if you remember, I had called them earlier GA of S and GT of S, meaning there are two transmittances from armature voltage to speed output and load torque to output speed. So if I show that, I will put here again that plus minus thing for convenience. Here is omega S, here is the load torque, and this is going through a transfer function which we have called GT of S, and this GT of S is what? It is going to be exactly this, 1 by j into S plus 1 by tau A divided by S squared plus AS plus B, and the other transmittance is from the applied voltage. So here is GA, the input to that is EA of S. So we have got rid of several blocks which were there earlier, and we are represented in a different way. But the rest of it I am going to keep the same, because I have here Ka by S, the amplification and integration operation. I have the tacho generator which provides the proportional negative feedback, and here I have the difference device as before. So here is ER, here is the tacho generator output, and it goes into this. So this is what the somewhat simplified block diagram looks like. And now we want to study the effect of Ka, this gain of the amplifier integrator, on the transient behavior of the system. We saw that it plays no role in the steady state behavior of the system. The steady state speed is simply such that ER equals K tacho generator into the steady state speed, irrespective of what the load torque is. So the motor will run at the desired speed irrespective of the load torque changes. So in the steady state there is no problem. But what about transient? When the load torque changes suddenly from one level to another, the speed is not going to remain constant. The speed is going to change for a small interval of time before it goes back to its old value. And it's the transient that we are interested in, and that transient we will see will be governed by this Ka. Now the analysis that I am going to do for this particular case can be generalized, and that gives rise to a method or an approach which is called the Root-Locus method. And this was introduced by an American engineer by name Evans in the 1950s. The method is called Root-Locus method. So what we are going to discuss applies to a more general class of systems, however, which look like the system that we are looking at, namely there is an output, there is an input, and there may be two inputs. One is the reference input or the true input, the other is the disturbance. Then you have transfer functions from them, but in between you have inserted a negative feedback which is proportional, and another feedback term or using or applied to that feedback signal is this integrator action. So what we have is called a proportional plus integral control system, or a PI control system. Of course, we can apply the technique to a system where there is no integrator, that is there is a straight or there is only an amplifier but no integrator. We will do that also. That is only the P controller, but we got into this whole thing because P controller was not satisfactory. So let us first look at the P plus I or PI controller. This is the block diagram that we have. And as I said earlier, we will look at the effects of the two inputs, the reference voltage input and the load torque input, separately instead of looking at them both at the same time. Now remember that we have a signal flow graph in which there are two inputs, there is one output. The relationship between the various signals is what is called linear. So the whole block diagram corresponds to a linear arrangement. And in fact, we had shown that omega S is equal to ER multiplied by something, plus TL multiplied by something else, and therefore we can consider the effect of ER and TL separately. This is sometimes referred to as the principle of superposition, but it is also known as the property of linearity of the system. The system is additive with respect to the inputs, and it's multiplicative or homogeneous with respect to scaling of the inputs. So because this is true, we can look at the effect of ER alone or the effect of TL alone. So let's look at the effect of reference voltage ER alone. So I can put TL equal to 0 as it were and only look at what remains. So what do I have? I have a simple forward path, there is a feedback path, and that's all I have. So I can think of a system, and this is what the Root-Locus method thinks about, where I have a transfer function, say GA of S, which produces an output omega of S, and there is this feedback arrangement ER. I can combine this Ka of S along with GA, because ultimately one is followed by the other. So I can put that Ka by S here itself. So I have a single block Ka by S into GA of S, and here is the feedback element K tacho generator. We are assuming that the tacho generator has been already chosen, so K tacho generator is not going to be changed, and we are looking at, or we are going to look at, the effect of the amplifier gain Ka on the transient performance of the system or on the behavior of the system when ER may change, and later we will see the effect when TL changes, right. So this whole thing can be thought of as a single transfer function G of S, and the transfer function in the feedback path, as I have told you, is called H of S. So we have the traditional standard block diagram for a feedback control system, which is a forward path. Now I am going to show that Ka separately, so I am going to write it as Ka into G of S. In the feedback path there is H of S, there is no variable gain there, and there is the simple difference device, ER is the input and omega is the output of the whole thing. Now I told you, and in fact now we can still apply the signal flow graph idea, and the work is so simple that we can derive the relationship between omega and ER almost immediately. And what is that relationship? Omega S divided by ER of S, and actually what we mean is omega S is equal to ERS into something plus another term which involves the load torque. We are only going to look at one term. So this, I will put that vertical line to remind us that we are only looking at a part of omega S. This is given by what? By Mason's gain formula, delta. What is delta here? 1 minus loop gain. What is loop gain? Ka into G into H. So the denominator will be 1 plus Ka G of S H of S, and the numerator is what? Forward path gain Ka into Ga multiplied by delta for that, but delta for that is 1, so it is simply Ka into G of S. So that's what we have. The transfer function of the closed loop system, or the overall transfer function as it is called, equal to Kag, the forward path transfer function, divided by 1 plus the forward path transfer function into the feedback path transfer function, or alternately 1 plus the loop gain or the loop transfer function, the transfer function going around the whole loop. Start with a point, go through Ka, go further through H, so when you are back, it's as if you have gone through a transfer function Ka into G into H, alright. So this is what the overall transfer function looks like. Now as we saw earlier, each one of these transfer functions Gs and Hs in general will be a ratio of two polynomials, and remember the terminology that we had introduced for the polynomials, n for numerator, d for denominator. So G of S I can write as G of S equal to Gn of S, the numerator polynomial, divided by Gd of S. Alternately some books may write n for numerator G of S and d for denominator G of S. Depends on which way you like to think about it. The G transfer function, its numerator, and the G transfer function, its denominator. That's what G of S is. Likewise H of S will be equal to H n of S divided by H d of S, the numerator part of H, the denominator part of H, or alternately the numerator of H divided by the denominator of H. So we think of the two transfer functions in terms of their numerators and denominators, and as you know by now, with the numerator part one associates what are called the zeros, and with the denominator part one associates what are called the poles. So my omega s by ER of s looks like Ka into G consists of Gn by Gd divided by 1 plus Ka into Gn by Gd multiplied by Hn by Hd. Here Gn, Gd, Hn, Hd are all polynomials which can be thought of as being factorized for our convenience if necessary. So this is what we have. Now we can simplify this further by getting rid of the Gd, Hd terms in the denominator part of the denominator. Therefore we will get omega s divided by ER of s equals Ka into Gn into Hd divided by Gd Hd plus K into Gn Hn. Ka into the numerator of the forward part transfer function multiplied by the denominator part of the feedback transfer function divided by the product of the denominators of the G and H transfer functions plus Ka times the numerator parts of the two transfer functions. Now the information about the G and the H transfer functions, as I mentioned to you earlier, is normally shown in the form of what is called the pole zero diagram. And so if here is the complex plane, on this complex plane I can show Gn by showing the linear factors, indirectly by showing the linear factors, by showing the zeros corresponding to Gn. Similarly, there will be zeros corresponding to Hn, there will be poles corresponding to Hd, and there will be poles corresponding to Gd. Once I do that, then on the pole zero diagram, then I can show the various poles and zeros. For example, and I am just doing it completely arbitrarily, this has no relevance to the example that we are looking at, although we will take that up immediately. There will be some zeros corresponding to the zeros of G and H. So they can be shown. For example, there may be a zero of G, so I will put here G n in bracket, that is, this corresponds to the numerator of G, so I can even put G here for this zero. The H transfer function may have a zero or it may not have. I will put, say, a zero here and I will say it is a zero of H, that is alright. So I have shown a zero of G and there is a zero of H. I have to show then the denominators of G and H. So I have to show the poles of G and I have to show the poles of H. Let us say here are the poles of G. So here is a pole of G, here is another pole of G, and maybe H has only one pole. Let us say here is a pole of H, so here is a pole of H shown like that. And so in this way I can represent my block diagram with Ka into G in the forward path, H in the feedback path by a pole zero diagram like this, and I will put here Ka as the overall multiplying scale factor, and I will assume that the numerator will consist of terms like s minus something into s minus something else, etc. They are all the zeros. Similarly, the denominator will consist of s minus something into s minus something else, they are all the pole terms. So we can assume that they have all been factorized with each linear factor having the coefficient of s equal to 1. With this, then, this pole zero diagram completely specifies all the information that we need to know about the block diagram that we started with. Alright, now what is our problem? We have this transfer function omega s by ER of s, and remember, now I am going to look at not only the steady state behavior, in fact I want to look at the transient behavior now. So suppose I assume that ER is a constant input from t equal to 0 onwards. So ER of s is, say, capital ER divided by s. Then from this I can calculate omega s, and then from that I can find out omega t. How do I do that? By using partial fraction expansion. So partial fraction expansion, how does that proceed? This denominator that we have, I have to factorize it, and once I factorize that denominator, then this ratio or fraction can be split into the partial fractions. Now what does the denominator look like? The denominator will perhaps look like this. Now look at the pole zero diagram that I have already drawn. Let me put some numbers here. For example, this pole of g may be at -1, the 0 of g may be at -2, the pole of h may be at -3, the pole of g, the other pole may be at -4, and the 0 of h may be at say +2, and the value of the gain Ka may be, let us say, 100. If that is the case, what is my denominator going to look like? Denominator is Gd Hd plus K times Gn Hn. Alright. What is Gd? G has two poles, one is at -2, the other is at -4. So Gd is going to be s plus 2 into s plus 4. Gd pole is at -1, so s plus 1 into s plus 4. That is the contribution of Gd. What about Hd? H had a pole at -3, so this will be multiplied by s plus 3, and that will correspond to Hd. So I will have this product of three factors, that is Gd Hd plus Ka. Ka is 100, so 100 times the numerator of G. The numerator of G, the 0 of G was -2, so it will be s plus 2 multiplied by the contribution of the numerator of H. This is at +2, so this multiplied by s minus 2. So the denominator is a polynomial which is Gd Hd plus Ka times Gn Hn. In this case it is a product of three terms, linear terms, plus 100 times the product of two linear terms. So what can you say about it as a polynomial? What is going to be its degree? There is this s three times, so I will get an s cube term from there, whereas from this I will only get an s square term. So the s cube term will remain, therefore I will have s cube as one of the terms in the polynomial, plus what? There will be an s square term, but where will that s square term come from? It will come from this, but it will also come from this. So it will be some term into s squared. What that is can be worked out, plus what about the coefficient of s? Again this product will contribute, this product will contribute, so something into s, plus what about the constant? From this I will get 1 into 4 into 3, that is some term 12, plus from this I will get 100 into plus 2 into minus 2, or minus 400. So it is going to be a cubic. If it is a cubic, then I can conceptually imagine factorized into three linear factors. So I can talk about its three roots. Now it is not going to be easy to factorize a cubic, as you know. In fact, I had asked you earlier and mentioned that factorization of the quadratic is very easy. We have learnt it back in school. Factorization of the cubic you may have learnt in your college algebra course, but you have most probably already forgotten it. It is difficult. If it is a quadratic, biquadratic, that is fourth degree polynomial, it is still more difficult, but there is a formula, and beyond the fourth degree there is unfortunately no formula. We have to use numerical techniques to find out the roots, but we can conceive that this cubic is factorized into three linear factors, and therefore we have three different roots. Once we factorize the denominator, then we can go back to the ratio, the numerator divided by the denominator. In this case, because Ka is 100, will be 100. Gn is the numerator part of G, so that will be into s plus 2 once again into Hd. Hd is the pole of D, therefore there will be s plus 3 divided by the same cubic in the denominator. So this is what the whole transfer function is going to look like. And now we can expand it in a partial fraction expansion. I have already mentioned that, and I have asked you to read up from your algebra book as to how to carry out the partial fraction expansion. You do that, of course this is going to be multiplied by ER of s, and for many inputs ER of s will also be a ratio of two polynomials. So actually therefore I will have a polynomial divided by another polynomial. I have to factorize the denominator polynomial, do the partial fraction expansion, and then do the inverse Laplace transform. From that I will get omega t. That is the approach. The hurdle is that I get a denominator polynomial which is such that it depends on Ka, and there seems to be no nice way of determining what its roots are. That is the problem. Now Evans in the 1950s thought about this problem and gave a qualitative approach which can be made partly quantitative to get some idea of what the roots of this complicated thing may be like. So, this is the Root-Locus method of Evans. Like the signal flow graph gain formula of Mason, the Root-Locus technique is useful for really understanding by you and me for small order systems. When you have larger order systems, the Root-Locus method does not become so useful if you and I have to do it by writing expressions, by manipulating them and so on. Fortunately, today we have program packages which can do all of this, and in fact which can plot what is called the Root-Locus for you. All you have to do is enter the information for the G and H transfer functions, specify the gain Ka or the gain of the transfer function or the system. The program will plot for you the Root-Locus. That is what happens for that value of Ka or as the value of Ka is changed. So, if we have a higher order system, not a polynomial of degree 3 or 4 but maybe 10, similarly the numerator also is more complicated, then factorizing, doing partial fraction expansion, finding the coefficients of the partial fraction expansion and all that, we can avoid it by using the programs which give you the location of the roots, or therefore we say that they plot, the program plots the Root-Locus. But to repeat what Hamming said, the purpose of all of this is not computation but insight. We want to understand what may happen, what can happen. Therefore, we will follow the Root-Locus method for a lower order system and see what one can get out of it. So, the problem then is, when I have a polynomial which looks like GD plus Ka into Gn Hn, what are going to be its roots? Not for just one value of Ka, because we want to see the effect of the gain, but when the gain is changed, what is going to happen to the roots? So, we are looking at the equation this equal to 0, or in other words we are looking at the roots of the polynomial on the left hand side. This kind of an equation is called a characteristic equation of the system. So, one says that we are finding the roots of the characteristic equation of the closed loop feedback control system, and that involves finding the roots of a polynomial which looks like this. There is a part GDHD which corresponds to the denominator of GH, there is a part GNHN which corresponds to the numerator of GH, and there is this multiplying coefficient Ka that multiplies the numerator part, and the sum of these two is the polynomial that we are looking at. In our case, this polynomial, the characteristic equation was s plus 2 into s plus 4 into s plus 3 plus keeping Ka and not writing 100 into s plus 2 into s minus 2, which results in a third degree polynomial, and therefore we are trying to find out its 3 roots as a function of Ka. What about this part of it? That part of it comes from the denominator of GH. So, that part comes from the poles of both G and H. What about this part? This part comes from the numerator of GH. Therefore, it comes from the, or it represents the zeros of the transfer function or the product GH, which is called the loop transfer function without the multiplying coefficient Ka. So, for this all we need to know the locations of all the poles and the locations of all the zeros in the loop transfer function. So, for our particular example then, the locations are, once again I will draw the diagram. There are 3 poles, one is at -1, another is at -3, and the third one is at -4. Of these, of course, 2 of them are coming from G, the other one is coming from H, but as far as our treatment is concerned, it does not matter which is coming from which. There are 3 poles. The other part are the zeros, one of them is coming from G, the other is coming from H. Once again, it does not matter which is which. So, I am just going to show here 1 0 at -2 and 1 0 at +2, and I want to look at it as Ka varies and not with Ka equal to 100 only. So, I will just write Ka there. So, this is the problem, or represented on a pole 0 diagram. The zeros are given, the poles are given. the gain Ka that sort of sits between the two is to be varied, what happens to the roots of the characteristic equation or the characteristic polynomial? That is the problem, and that is the problem which Evans solved, and he gave a graphical technique, therefore an approximate technique, or a technique really to get some idea of what is going to happen rather than a technique for exact computation. That is the Root-Locus method. Now it can come as a surprise that just looking at this, and of course applying one's thinking, following the steps of Evans, there is quite a bit that we can say about the roots. For example, if Ka, the gain Ka is very small, by that we mean I am not going to put Ka equal to 0, because if the gain is 0 then there is nothing in the forward path, so I will get 0 output, but Ka is very small, so Ka is very close to 0. What do I mean by very small? I can't really say, but think of the limit therefore as Ka is decreased. Where will be the roots of the characteristic equation? That is one case. Second is you make Ka very large, maybe 10,000, not in practice of course, but in theory, in our study. So I will put it as Ka equal to or nearly equal to infinity, meaning that if Ka is very large, where will the roots of the characteristic equation be? Evans gave rules, two rules, from which you can get this information. For values of Ka which are not very small nor very large, in other words for normal values of K, therefore which lie between 0 and infinity, you have to do some more work in order to find out where the roots will be. But the two extremes, approaching 0 and approaching very large gain, that is infinity, there are two very simple rules that tell you what happens to the roots. Now of course that depends on whether the number of poles is equal to the number of zeros, or is greater than the number of zeros, or is less than the number of zeros. So if I write n p for the total number of poles of G and H, n z for the total number of zeros of G and H, in our case there are 3 poles of G and H together, so np is 3, there are 2 zeros of G and H considered together, so nz is 2, np is greater than nz, the number of poles is 3, the number of zeros is 2. There can be a situation where the number of poles is equal to the number of zeros, and in principle you could consider a situation when the number of poles is even less than the number of zeros. So one has to consider these 3 cases. Usual case is this: the number of poles is greater than the number of zeros. For our motor problem, that is exactly what is happening. The number of poles is greater than the number of zeros, because you remember the forward part transfer function G had a quadratic in the denominator, therefore only 2 poles. The feedback transfer function was only KTG, so no pole nor 0, it was just a coefficient. So the loop transfer function GH, or the loop gain GH, had only 2 poles and no zeros. So NP was 2 and NZ is actually 0. So certainly NP is greater than NZ. If this is the case, if the number of poles is greater than the number of zeros, then one of the rules of Evans says that when the gain is very small, the roots will be very close to the poles. So for Ka very nearly equal to 0, the roots are near the poles, and the smaller the Ka is, the closer the roots will be to the poles of the loop transfer function. And therefore one can say that if you think of starting at 0, Ka equal to 0, and then gradually, as if you have a knob by which you are changing the gain, you increase Ka starting from 0 slowly, and you keep on increasing, and in theory you increase it indefinitely, make it very large. The roots are not going to stay unchanged. When Ka is small, the roots will be having some values. When Ka is very large, they will have some other values. When Ka is say 50, they will have still other values. When Ka is 1000, there will be still some other values. So one can think of the roots changing their location as Ka is changed. And Evans's method enables you to sketch or get some idea of what this would look like if you were actually going to plot the root locations for various values of Ka, and therefore it is called a root locus plot, or we could simply call it the root plot, but as in coordinate geometry one uses the word root locus. So the root locus plot is just a plot of the location of roots of the denominator of the closed loop transfer function as the gain Ka in the forward transfer function is varied from 0 to infinity or between 0 and infinity. That is, the gain may be considered to be very small, it may be considered to be very large, and then we want to look at the values in between. So one of Evans's rule, the first one for example, will say that if the number of poles is greater than the number of zeros, then for small value of Ka the roots are very close to the poles, and therefore one can say that the root plot or the root locus plot or the plot of the roots starts at the poles. There are 3 poles, so there will be 3 branches of the root locus, and this is the terminology that is used. There will be 3 branches of the root locus which will start at the poles. It's a very simple rule, not very difficult to remember. The root locus branches or the branches of the root locus plot, and there are branches, why? Because there are 3 roots in this case. In general there will be more than 3 or less than 3 roots, not just one root. The characteristic equation is a polynomial, not of degree 1 necessarily. Therefore there will be more than one root. Therefore there will be branches of the root locus. So one says in this case that if Np is greater than Nz, then looking at our earlier formula here, for example, we can see that always there will be 3 roots. So the root locus will have 3 branches. So the number of branches of the root locus will be equal to the number of poles of the loop transfer function, and one says that these branches will start at the poles, meaning that when Ka is very small, the roots will be very close to the pole locations, and in theory when Ka is 0, then what does the polynomial become? This part is already gone, it is simply the part that corresponds to the poles. So the roots are at the poles, but of course this is not of interest because Ka equal to 0 will simply give you a 0 output. But no harm in saying that the root locus branches start at the poles for Ka equal to 0. Now what happens when Ka becomes very large? The answer is there will be branches or there will be roots which will be very close to the zeros for large value of K. Now I have 2 zeros, so there will be 2 roots which will be close to these 2 zeros, but the number of roots is 3. So what about the third root? Now for the third root, one says that it has an asymptotic behavior and something will happen to it as K tends to infinity. It will not be near the zeros of the transfer function, but the third root or the remaining roots will be in fact going far away in the complex plane with an asymptotic behavior, and therefore one can talk about what are called asymptotes to the branches. And how many asymptotes will there be? Well, here we have Np equal to 3, so there are always 3 branches of the root locus, all 3 of them start at the poles. Nz equal to 2, so there will be only 2 of them which will be close to the zeros, and therefore one says they will end at the zeros, and the third branch will approach an asymptote, and Evans gave a rule for determining the number of such asymptotes and the location, so that one can draw the asymptotes and expect that for large values of gain K, the roots will be close to the asymptotes. In our particular example, the number of asymptotes is only 1, and I will give you the formula very soon. In this case, the asymptote, which is only 1, will really consist of the negative real axis going towards the negative real part becoming infinite end. So this is the asymptote. That means what? the third root will lie close to this asymptote, and therefore the third root will become large and negative and very close to being real, whereas the other two roots will be close to the two zeros of the loop transfer function. So the three roots will start off at the three poles. So think of some curve starting from here, the branches of the root locus. Then we don't know what happens to them right now. Two of them end up at the two zeros, so they will end up here. The third one will go towards the asymptote, and the asymptote is going towards the negative real axis, or the negative real axis is the asymptote. So the third root will approach the negative real axis going towards infinity. So the third root will become very large, negative real, or very close to being a negative real number, whereas the other two roots, one of them will be very close to -2, the other root will be very close to +2. So think of it, just two very simple rules which, depending on NP and NZ, tell you that the number of roots will be so many, therefore the root locus will have so many branches, and where will the branches start, that is for Ka very close to 0, where will the roots be, where will the branches end, that is for Ka very large or approaching infinity, where will the roots be. If Np is greater than Nz, the number of branches is Np, all of them start at the poles, among them Nz will end at the zeros, and the difference Np minus Nz will approach asymptotes. So the number of asymptotes will be Np minus Nz. In our case, there are three poles, there is only one zero, therefore there are two zeros, therefore there will be only one asymptote. If Np is less than Nz, the situation will be reversed. The number of the degree of the polynomial will be the degree Nz, that is of the zero part. The branches will be the number of zeros. The branches will all end at the zeros, but Np of them will start at the poles, and the remaining will start from a region of the z plane which is very far away from the origin, and therefore they will sort of come in from infinity, starting being very close to again asymptotes. So one can find out the position of the asymptotes in both the cases. In the special case, when Np equals Nz, now that's not a very common case, but it is useful to think of it. When Np equal to Nz, then what? Then the number of branches is simply each one of them the same number. So they will start at the poles, they will end at the zeros, and therefore there are no asymptotes. So there will be no roots which will be very large out there in the complex plane or towards infinity, as one calls it, whether for small value of k or for large value of k. For all values of k, the roots will not become very large, although they may become large, but they will not increase to infinity, or they will not, for very low gain k, as you reduce the k, also increase to infinity. They will start at the poles, they will end at the zeros, equal in number. So these are the two simple rules of the root locus, or three if you wish. The number of root locus branches is the larger of Np and Nz. Secondly, the root loci start at the poles, some of them, if not all of them. The root loci end at the zeros, some of them, if not all of them. And the remaining branches either go asymptotically out in the complex plane if Np is greater than Nz, or they start from infinity, as it were, that is being very large amplitude in the complex plane, and as k increases from 0, they will come closer to the location of the zeros. So these are the two simple rules of the root locus method. We will be looking at some more rules of the root locus method, but in order to emphasize the power of the root locus method, let me give you the solution that the Evans root locus approach is finally able to give you. I have this pole 0 diagram. I am going to start at these three poles, I am going to end at these two zeros, and one branch is going to end towards the negative real axis. Alright, now what is going to happen in between? I am going to say something which we will look at in detail. So there will be some more rules which have to be looked into. there is a rule that determines the real axis portions on the root locus. That is, what part of the root locus can be expected to lie on the real axis, or the other way rather, what part of the real axis will correspond to some root location for some value of k. Now, there is a rule which is a little difficult, but not that difficult, which can be used to determine the parts of the root locus which are on the real axis, or the parts of the real axis which belong to the root locus. So, this rule is called a rule for determining the real axis portion of the root locus, a portion of the real axis which belongs to the root locus. Now, there is a simple rule for that requires looking at the pole 0 diagram, looking at the real axis, and then observing something. And I will not tell you what it is right now, but I will simply give you the rule as it is. In this case, using that rule, this portion of the real axis will belong to the root locus, and I am going to put an arrow on it to indicate that as k increases, there will be a root which will be here, then it will move, that is, for a larger value of k the root will be here, for still another value it will be here, and so on. For very small value, of course, the root will be very close to -1, for very large value of k it will be close to 2. So, one branch of the root locus will simply look like this, and one says it starts at -1 and goes towards 2 along the real axis in this direction. What about the other two branches of the root locus? Well, again, some further rules will tell you that there will be a branch, or there will be a portion of the root locus here between these two poles and nowhere else now on the real axis, and therefore there will be a breakup of the two branches. The two branches will go towards each other and then they will break up, or things of that sort. Now, this is something which we will have to look into, but it is interesting that simply from the pole 0 diagram, with the help of some very simple rules, one can get some idea of the branches of the root locus, what they are going to look like, and then from that get some idea of what the response of the closed loop system for certain inputs is going to be like. We will be able to conclude, for example, that if the gain is Ka is too large with integral feedback, then the system will oscillate, that is, it will involve oscillations. The speed, when it changes momentarily before going back to the same value, will oscillate. Now, if that behavior is tolerable, well and good. If it is not, then the value of Ka that you have chosen is too large, you will have to reduce the value of Ka. Information like that can be obtained by looking at the root locus plot as given by Evans and his rules. So, that is the thing that we are going to look at next. We will be looking at Evans's root locus method.